Okay, now we are going to go through ease of hydrolysis. So this is actually one of the, I would say, favorite questions that a lot of people see in papers because it's more or less free 4 or 5 marks. Because this is really just a direct testing of LO 11.8 F over here. Yeah, here. And this can be found in section, I forgot what section, 6 point something. Yeah, 6.3 of your lecture notes on carboxylic acids and derivatives. So it shows you this giant table over here, and you see that for each one there's an electronic factor and a steric factor. So more or less this entire table in your lecture notes is just the answer to this question. But I want to point out here, right? You notice that here they give a reaction with Ag and O3. And this actually reminds you of something in halogen derivatives, right? So if you go to your halogen derivatives lecture notes, you will see that there's this section here on distinguishing tests. And it's about the um, silver halide precipitate. So I am just going to very quickly go back to halogen derivatives for this one, about the steps for the distinguishing test that you need to know. And you can see that the three precipitates are actually of different colors. So if you have a chloroalkane, RCl, you're going to get a white AgCl precipitate. For a bromoalkane, the AgBr precipitate is cream. Now, I think we should know if we have done enough inorganic QA up to this point, both in the past couple of months and also in Set 3, Set 4, when we also did QA for anions, we will know that this white PPT and this cream PPT can be a bit hard to discern at times. That's why the lecture notes have added this additional table here, row in this table here on the solubility of the precipitate in NH3. And the reasons for solubility are insolubility equilibria, because basically this complex ion, actually this should be a reversible arrow, this is an equilibrium, but depending on the identity of this X, the position of the equilibrium will lie either a bit to the left or a bit to the right, and therefore that affects the solubility. Okay, so I don't want to digress too much here. I'm just going to go on to answering the question. Now, you don't need to state the electronic and the steric factor for both. In fact, right, the recommendation is to just stick to the electronic factor. If this is a paper 3 question, let's say Choi Touchwood, they give you like 6, 7 marks on this question. Maybe at most 5 or 6 marks lah. Then no choice, you need to know the steric factor also. But typically, they will only give you 3 at most 4 marks because they can't invest so many of their precious marks in one LO1. This is a very commonly tested LO, but honestly, in the grand scheme of things, it's quite a minor LO. So they hopefully won't devote too many marks to this. So you just need to know the electronic factor for relative rate of hydrolysis. So you can see that they want you to mainly talk about this particular row in the table. So the first step, of course, is to order them. I think I covered in, basically the structure is very similar to the video in the hydroxy compounds folder about comparing acidity. So obviously, just ordering them correctly is going to get you 1 mark. Okay? Now, we know that in the lecture notes, the terms that used to refer to these 3 compounds are aryl chloride, alkyl chloride, and acyl chloride. But throughout this question, I'm just going to refer to them by their names lah. So this one is obviously chlorobenzene. This one, we call it benzyl chloride because this is an alkyl chloride, but the benzene ring is bonded to the alkyl carbon. So this is benzyl chloride. And this one is an acyl chloride. So remember, acyl chlorides, we end with an ol, right? Like ethanol chloride. So this one is benzoyl chloride or benzoyl chloride, however you want to pronounce it. It's just spelled like that lah. OYL chloride, in case you need a bit of revision on nomenclature. But anyway, ease of hydrolysis, right? It's all about to what extent does this CCl bond cleave? So if we look at this CCl bond here, does this cleave easily? No. It's very hard to cleave. Why? Because it has partial double bond character owing to the delocalization of the lone pair of electrons of the Cl into the benzene ring. We know about the delocalization phenomenon from phenol and how that affects acidity, so I'm not going to elaborate on that here. But yeah, partial double bond character, and therefore this is the strongest. This C-cell bond is the strongest and therefore cleaves least easily. That's why this has the lowest rate of hydrolysis. Now, this alkyl chloride, benzyl chloride, uh, anyway, I forgot to say. So once again, if it's 4 marks, each of these will give you 1 mark. Okay, is the mark breakdown here? No, they don't say. And this is quite an OTYS question, so I don't think I can find the original question and see how many marks it was worth. But presumably 4 marks are based on the model answer that I have here, which you can just look on the Google site for answers. Okay, so in this case, next one is to look at benzyl chloride, my alkyl chloride, as compared to benzoyl chloride, my acyl chloride. So I think I'm going to just expand this part a bit so that it's clearer to you. I have CH2Cl. Okay, so I'm interested in this Cl bond here. Does this CCl bond cleave easily? And you see that this carbon is obviously slightly electron deficient because it is bonded to an electron withdrawing chloro group. So as a result, because it has one highly electronegative atom bonded to the carbon atom, it cleaves moderately easily because there's some polarization of the electron count here. But on the other hand, if we expand this part here, we will see that it's just COCl. It's trigonal planar here. Okay. And this C, right, I'm interested in, can this CCl bond cleave easily? You'll notice that this C is bonded to 2 highly electronegative atoms that withdraw electron density. So this one is very, very delta plus. This one only a small bit of delta plus because it's only bonded to 1 highly electronegative atom. So this one is going to be more electron deficient as compared to the C atom here in this chloride, which is less electron deficient, and so as a result, this is going to be less susceptible to nucleophilic attack because it is less delta plus. This one is more delta plus, so it's more susceptible to nucleophilic attack. And this nucleophilic attack is what causes the CCl bond to cleave, which is what we call ease of hydrolysis, basically. And actually, now that I'm talking about it, right, I'm just going to elaborate a bit on the steric factor. But I think this should be quite intuitive to us now that we've covered so many mechanisms in organic chem. This one, what's the geometry about the delta plus carbon? This is tetrahedral. This one, what's the geometry about the delta plus carbon? It is trigonal planar. So obviously, this one got less steric hindrance than this one. Okay, I think that also explains the ease of nucleophilic attack of this delta plus carbon. So yeah, you can see the worded explanation here. Planar, trigonal planar, actually. Not sure why your lecture notes don't say trigonal. And this one is tetrahedral. And then this one, the steric factor is because the aromatic ring is bulky, so there's a lot of steric hindrance. And also, you need to remember the delocalized pi electron cloud, or actually any pi electron cloud, whether it's the localized pi electron cloud of an alkene or the delocalized pi electron cloud of a aromatic ring, it is going to be electron rich. So the E minus cloud itself is nucleophilic. So obviously it's going to repel any nucleophiles that approach. I think that's it for this question. Next one is going to be on basicity, which I'm going to put in the folder on nitrogen compounds to keep it topical. And I think that's it. Bye bye.